Hi there, welcome to lecture 20 of Fox, where we're going to continue talking about expected values, because it's that important. Okay, we're going to introduce a few more sophisticated techniques that makes it much easier to compute expected values. Specifically, we're going to talk about the expected value of a sum, okay, and we're going to introduce this concept of an indicator random variable, which when used in conjunction with the expected value of a sum can make computing expected values much easier. Okay, but before we get going, let's recap what we talked about last time, which was the expected value. So the expected value is a summary now of the random variable, the entire PDF of the random variable, which itself is a summary of the complex experiment. So complex experiment, take a measurement, that's the random variable, take the expected value of the random variable, okay, and that's a mathematical formula that equates in the long run to, if you repeated the experiment many times, what would the average be? Okay, so that's the mathematical expectation. It's just a formula. We can compute it. Sometimes the computation is hard, and we did several examples. We talked about the sum of dice, the Bernoulli, the uniform, the binomial, and the waiting time. The binomial and waiting time are very important. Okay, when you try something a fixed number of times n, and you count the number of successes, or you try something where you have a certain probability of success, and you keep trying until you succeed. Okay. Then we introduce the concept of a conditional expectation, analogous to a conditional probability. Okay, so you update an expectation when new information arrives. Okay, by using the updated probability. That's not that hard. Okay, and then we talked about the law of total expectation, analogous to the law of total probability. So it makes it easier sometimes to compute an expectation by breaking it down into cases and then using the law of total expectation. What am I saying? It makes it much easier sometimes. Okay, so master the law of total expectation. Okay, so today we're going to talk about the expected value of a sum. Okay, and there are also more sophisticated techniques like iterated expectation, expected value of a product. Okay, so you can look at the textbook for those more sort of complex ideas, complex concepts. We will focus on the expected value of a sum. Okay, we'll see how we can use the expected value of a sum and the law of total expectation to do build-up expectation, and then we will introduce this concept of indicators, which together with the expected value of a sum can make computing expectations much, much easier. Okay, and so let's begin. Let's go to the board. We're going to be talking about the expected value of a sum. Okay, but before we get going, let's warm up a little by computing an expected value. Okay, and let's talk about something that you might have heard about, seen all around you, the lottery. Okay, and this thing happens, let's say, roughly every week, and the rules are that every week, let's say, you can buy a lottery ticket for $1. Okay, so it means you pick a number. Okay, and what's the number? The number you pick is a set of 5 numbers between 0 and 70. So 0 to 70, you pick 5 numbers. Okay, and you also pick the order. And now if your 5 numbers match the 5 numbers drawn at the end of every week, well, then you win. Okay, so we draw 5 numbers. Okay, and so what are how many possibilities are there for this outcome? So there are 71 choices for the first number, and we draw 5 numbers, so 71 raised to the power 5. Let's just say that's approximately equal to 2 billion. So the chances that your number is one of those 2 billion numbers are 1 in 2 billion. So the probability to win is 1 in 2 billion. Okay, that's pretty slim chances. Okay, now, but however, every now and again you find out that someone won the lottery. So what's going on here? It's not that you're becoming astronomically lucky. It's that many people are trying. So let's assume that there are 20 million people. Okay, and each of them buys a lottery ticket every week. Each buys a ticket every week. Okay, and if someone wins, they get whatever's in the pool. So if they lose, it goes into the pool, and some fraction of this pool is siphoned off by the state to fund public education and roads and so on and so forth. So this is a way in which states can make money. It's a government-sanctioned piece of gambling that allows people to pay a little bit of money for a big ticket payday, but at the same time it allows states to gradually generate a little bit of revenue to pay for public works projects and education and things like that. Okay, so now you have the tools to answer questions like how many weeks will it take on average for someone to win the lottery? Questions. How many weeks weeks on average for someone to win. Okay, we're ready. You have the tools to answer this question. I'm not going to answer this question. I'm just going to say that, typically when somebody wins, so the lottery has typically built up to, let's say, around 200 million. Okay, so approximately 200 million is the payday. Okay, so 2 winnings, let's say, is about 200 million. That's a little bit optimistic, but I'm just approximating here. Okay, so now if they say that that's the current, pool. Okay, and so now if you play this game, your chances of winning are 1 in 2 billion. Okay, so what are your expected winnings? Well, what's your expected gain from playing the lottery? Well, you buy a lottery ticket, you spend $1, okay, and then you win 200 million with probability 1 in 2 billion, and you win 0 with probability 1 minus 1 in 2 times 10 to the 9. So 1 minus 1 in 2 billion. Okay. So if we let a random variable x denote your winnings, so then x, denote your winnings, is, we can ask, what is the expected value of x? Okay. And it's going to equal, with probability, 1 in 2 billion, the amount of money that you have won, okay, is minus 1 for the ticket you bought plus 200 million. So it's minus 1 plus, 200 million. Okay, with probability 1 over 2 times 10 to the 9, with probability 1 in 2 billion. And the amount that you have won is minus 1 with an overwhelmingly large probability, plus minus 1 with an overwhelmingly large probability of 1 minus 1 over 2 times 10 to the 9. Okay. And so we can see, okay, that your expected winnings, so this is minus 1 times, 1 in 2 billion, okay, plus minus 1 times 1 minus 1 in 2 billion, so this is equal to minus 1, so this term and this term are equal to minus 1, okay, plus, 200 million divided by 2 billion, so that's 1 in 10. Okay, so this is equal to minus 0.9. So your expected winnings in such a lottery are approximately minus 90 cents. Expected winnings is approximately equal to minus 90 cents. So on average, many people are playing this lottery, so on average they're all losing about minus 90 cents. So you see the state is, and where does that minus 90 cents go? It goes to the state in some sense, okay? But we won't get into the details, the fiscal details of how, lotteries are using the money and who gets the money and so on and so forth, okay? Just from your perspective, the lottery is a losing, proposition. In fact, you're losing 90 cents, for every, for every time you play the lottery. But people still play the lottery. Why? Because, there's 90 cents. I'm losing 90 cents in change, through the holes in my pockets every week. So I might as well use that money to play the lottery, right? And why? Because the 90 cents is not really worth that much to me. But if I win the 200 million, wow, my entire life changes. Okay, so that's why people play the lottery. It's not that they don't know that on average they're losing money. It's just that, it's a little bit of money now, which I don't really care about. And if I win, it's just, it's this promise of, greatness in some sense. Okay, it's worth investing a little bit of effort if there's a promise for a big payday. Okay, now, so you get all worked up by lotteries, and you say, well, what if I played the lottery in New York and the lottery in Massachusetts? So you buy a ticket for New York, and you buy a ticket for Massachusetts. Okay, and so your total winnings, let's call it T, is equal to let's denote by T sub New York your winnings from New York, and T sub Massachusetts your winnings from Massachusetts. Okay, so your total winnings is the sum of these two winnings. Okay, and so you might think, well, whatever I win here is whatever I win here, whatever I win here is whatever I win here. These are two sort of totally independent entities, and I expect to win in total the sum of whatever I expect to win here plus the sum of whatever I expect to win here. Intuitive. Okay, so your expected total winnings, which is expected value of t, you expect it to be, I mean, you sort of intuition suggests that these are, New York and Massachusetts has nothing to do with each other. Okay, so it should be my expected winnings in New York, okay, plus my expected winnings in Massachusetts. Okay, and so that's where we're getting towards today. So expected value of a sum. But now let me throw in a wrench. Okay, suppose you buy 2 tickets for the New York lottery. Okay, now what happens? Okay, so let's call those tickets T1 and T2. Okay, now the expected winnings for ticket 1 is 90 cents, minus 90 cents. The expected winnings for T1 is minus 90 cents. And the expected winnings for T2 is minus 90 cents. Here we just imagine that it's this lottery that's being played. And now you might think, well, since I bought 2 tickets, what are my expected winnings in total when the lottery is run? Okay, what are my expected total winnings? Okay. Now you think, oh my goodness, it's going to get complicated because, when one ticket wins, the other loses. You cannot win with both tickets. Okay? Whereas, in the New York and Massachusetts example, you can win with both tickets. Okay? Whereas here, if one wins, the other doesn't win, you both can't win, and so on. It looks more complicated. Okay? Because these tickets kind of depend on each other. Okay? Well, it turns out it's not any more complicated. And that's what's surprising. And that's what we're going to discuss today. Your expected total winnings, the expected total winnings is still the sum of the expected winnings. Expected value of T1 plus the expected value of T2, which is equal to minus $1.80. So if you buy 2 tickets in the same lottery, you're expecting to lose $1.80. If you buy 2 tickets in 2 different lotteries, for example, from different states, you're expecting to lose $1.80 in both cases. Okay, and so let me summarize that, and we're going to prove it. Okay, so theorem, and we'll prove it for the case of 2 random variables, but the argument holds in general. Theorem. Okay, and now this is a very important theorem, and sometimes we call it the linearity of expectation. Okay, and this is a very important theorem. Okay, and you may ask, when does it hold? Always. Okay, always. Okay. Modulo the fact that it's a finite sum. Okay, so infinite sums are tricky, but if we in both of these examples of the lotteries, our total money made is the sum of 2 things. Okay, so in general, let us define the sum of random variables. So even though I'm stating this as a theorem and I'm describing some things like the sum of random variables, and I'm going to put it all in the theorem just so that it's all in one place. So define the sum of random variables. As follows. Okay. So let's say you have random variables x1 and x2. x1 and x2 are random variables. Okay. Then we can define a new random variable. Define a new random variable. New random variable x, which is, let's call it, a1 x1 plus a2 x2. Okay, and you say, what? I measured temperature and pressure and I'm taking the sum? Okay, because remember, random variables were measurements. So now we need to go back to the formal definition of what it means to be a random variable. So a random variable is a function, x1 is a function that maps, my outcome space to the real numbers. And x2 is a function that maps my random variables to the real numbers. Okay, so we can talk of x1, taking as input some outcome and outputting a real number. Okay, and x2 as taking some outcome and outputting a real number. Okay, so this is where it's very important to realize that a random variable has a very formal definition as a function from the sample space to the real numbers. Okay, and I can take the sum of two functions. I can define a new function, which is the sum of two functions. So x of w. So x is a new random variable. It's a function that maps my sample space to the real numbers. And I'm going to now define it for you. Okay, x, when it sees the outcome w, simply outputs a1 x1 of w plus a2 x2 of w. And now that's very well defined. So basically, I'm defining a new function as the sum of two functions. Okay? And we've seen this many times. You can define functions in terms of other functions. That's what it means to take a sum of random variables. Okay. So even though I'm defining this sort of peripheral stuff inside the theorem, it's useful to have it inside the theorem so that you know what a sum of random variables is. So now what does the theorem say? The theorem says that the expected value of x, okay, is equal to the expected value of a1 x1 plus a2 x2, okay, which is equal to a1 times the expected value of x1 plus a2 times the expected value of x2. Okay, so now we say that this is a linear combination of x1 and x2, and the expected value of a linear combination is that linear combination of expected values. Okay. In particular, the expected value of a sum is equal to the sum of expected values. So when a1 and a2 are both 1, it's equal to the sum of the expected values. Okay, and that's very important. Now, because the expected value of a linear combination is that same linear combination of expected values, this is called the linearity of expectation. So that's the theorem, okay? Or in words, okay? An expected value of sum is equals sum of expected values. The expected value of a sum is the sum of expected values. That's poetry. Memorize it. The expected value of a sum is the sum of expected values. The expected value of a sum is the sum of expected values. Put it in your head and keep it there forever. Okay. Now, mathematically, what this means is that you can take an expectation into a sum or pull it out of a sum. Okay? So constants, okay, and addition can be taken outside an expected value. Okay, and you might ask, what the heck does that mean? Because look, here we have constants and an addition inside an expected value. And now I've taken the constants outside, and I've also taken the addition outside. Okay? And if you think back, when we did summation, we had the constant rule and the addition rule. Okay? And that's exactly what is going on here. That, a constant can be pulled out, so an expected value is like a sum. Not like a sum! Remember, we defined it last time. It is a sum. So an expected value is a sum, and essentially what's going on here are the constant and addition rules for summation, that you can pull a constant outside of an expected value because an expected value is a sum. And you can take the expected value of terms added together as the addition of those individual terms. So these are exactly the rules that we had for computing summation. Now we are seeing them again when we're computing expected values of sums, and that's because the expected value is a sum. So let's prove this. Okay, so proof. Okay, now we'll use the sample space, version of the expected value, which I asked you to sort of convince yourself of from last lecture. So what is the expected value of a random variable x? 1. Okay, it's the sum over your outcomes in your sample space, okay, of, the value times the probability of the value. Okay, that's what the expected value is. Okay. It's a little bit easier to work with the definition of the expected value through the sample space because all the random variables are defined on the same sample space. But the random variables may take on different values. But they're all functions defined on the same sample space. The expected value of x2 is equal to the sum over your outcomes, the value of the outcome, i.e. the measurement, this is x1 and this is x2, the value of the outcome times the probability of the outcome. Okay, and the expected value of x is equal to the expected value, the sum over outcomes, x of w, p of w. Okay, but now this is where the definition of the sum, this function which is the sum, comes into play. So this x of w is this linear combination. So this is equal to the sum over your outcomes of a1 x1 of w plus a2 x2 of w times p of w. Okay? And where's that coming from? X of w, we defined it here. We defined what it meant to be the sum of random variables. Okay, but now it's straightforward use of the rules for summations. Okay, so this is equal to the sum of, we can multiply the p of w. So there are actually two terms here, a1 x1p, a2 x2p. Okay, and we're taking a summation of two terms added together. So, the addition rule says that this is the sum from over w in omega of a1 x1 of wp of omega plus the sum over omega in your sample space a2 x2 of omega p of omega, and this is the addition rule for sums. Okay, and now I can apply the constant rule. I pull out the a1, I pull out the a2 from the sums. Okay, so this is equal to a1, the sum over outcomes in my sample space x1 of the outcome, p of the outcome, the probability of the outcome. So this is an expected value plus, a2, I pulled out the constant a2, sum over my outcomes, x2 of the outcome, p of the outcome. Okay, but now I see here I have the expected value of x1, and now I see here I have the expected value of x2. So this is just equal to a1 times the expected value of x1 plus a2 times the expected value of x2. And that's the end of the proof. Okay, it's a very short proof. It's exactly, analogous to the constant and addition rules from when we computed sums. Okay, and now, let me just point out that when you look at this proof, you'll see that it'll hold no matter how many terms are in the sum. So, I can just apply the addition rule for if I have k terms in the sum. So if I take the sum of k random variables, I'll just have k terms in the sum. So I'll have, k terms added together. So I can break them all apart and get individual sums, and then I'll get individual expectations. Okay. So this easily extends to more than two random variables, to sums, to a sum of more than two random variables. Okay, and so there's the proof. This very fundamental result. I'm going to state it again because it's poetry and you should memorize it. The expected value of a sum is a sum of expected values. The expected value of a sum is a sum of expected values. And there's the more complicated version, which just says that, it also works if you have constants multiplying the random variables before you take the sum. Okay, so that's called the linearity of expectation. Slightly more sophisticated version, but the more basic version, the expected value of a sum is a sum of expected values. memorize that. Here's the proof. Now let's do hordes and hordes of examples. Okay. Just to show you how this makes life so much easier when it comes to computing expected values. And why is it so important to compute expected values? Because you've done this complicated experiment. Okay. This complicated experiment has a complex outcome. Okay. We're not interested in the complex outcome, so we summarize of a measurement in a random variable, a function from the outcome to a number. Okay. So we've summarized the experiment in a random variable, and now we are still, looking at the random variable and its entire PDF and saying, it's too complicated. Can you give me one number which summarizes the experiment? That's the expected value. Okay. In some sense, it's what you expect to happen. Okay. It's the expected measurement. In a more formal sense, if you repeated the experiment many times, okay, the expected value is what you will see on average. Okay, if you take the average of the values that you measure. Okay, so expected value is important. Okay, and now we just see that if you have a sum, it's almost as easy as just computing the individual expected values. Let's do examples. Let's erase. Do examples. Bam, bam. Let's knock down example after example after example. Whew. We're now going to use this theorem on the expected value of a sum to recompute some of the expected values we did the hard way, i.e. using the formal definition from last lecture. Okay, and we'll even do more complicated versions of that. Okay, so I'll erase this little tidbit that, this formula applies even if you have more than two terms in the sum. And let's now do a bunch of examples. Okay, so let's start with the sum of 4 dice. So you roll 4 dice. So 4 independent fair dice, and take the sum. So x is the sum. The measurement we take is the sum of the values. Okay, and we might ask, what's the PDF for x? So the PDF for x. So if we take the possible values of the sum, okay, and what's the probability? So the minimum sum is 4, and the maximum sum is 24. So you have 4, 5, 6, 7, and so on. And it's a uniform sample space, so 1 over 6 to the power 4, that's the number of outcomes, 1296. So there's one way to get a 4, so 1 over 1296. There's one way to get a 24, 1 over 1296. And then a 5 is 4 over 1296. And then 6 is 10 over 1296. And now you might ask, how many ways are there to roll a 7 with 10 dice, and so on and so forth. So you can compute these probabilities, and then you take the expected value of x, so the expected sum of 4 dice, you do 4 times 1 over 1296 equals 1 over 1296 times 4 plus, 4 times 1 plus 5 times 4, 4 times 1 plus 5 times 4 plus, 6 times 10 plus, oh, wow. Okay, so exercise. An exercise in masochism. Compute this expected value by first computing the PDF, and then computing the expected value using the formula, okay, which is the weighted sum of, you take the value, weight by the probability, and add. So exercise, compute PDF, the full PDF, and then the expected value of x, as in above. Okay, so it's a relatively straightforward exercise, although tedious. Okay, but we're going to get this expected value almost instantly by noting that if you have your 4 dice, x1, x2, x3, x4, and you let x1 to x4 indicate, the roll that each of the 4 dice got. So what was the roll on the first dice, roll on the second dice, third dice, fourth dice. So these are all random variables that can be computed on the same sample space. Okay, so when you roll 4 dice, there's a value on the first, that's a random variable. There's a value on the second, that's a random variable, and so on. And my x is equal to x1 plus x2 plus x3 plus x4. And the theorem says that the expected value of x is equal to the expected value of x1 plus the expected value of x2 plus the expected value of x3 plus the expected value of x4. Okay, and we know that the expected value of a dice roll, a single dice roll, we computed it last time, is 3.5. So this is 3.5 plus 3.5 plus 3.5, 3.5 plus 3.5, okay, which is 4 times 3.5, 4 times 3.5, which is equal to 14. Boom. So when you compute this expectation as your exercise, you should get 14. In fact, we can easily compute the expected value for n dice rolls. N dice rolls. Okay, so the expected sum for n dice rolls is just n times 3.5. Okay, now you try to compute the PDF for even the sum of 10 dice rolls, and you'll see how hard it is. But the expected value, easy to get using that theorem. That's how powerful that theorem is. Okay, now let's do some other examples. Or the binomial. Okay, so remember the binomial. Okay, you have n trials. So let's call each trial, x1, x2 up to xn. So x1, x2, x3 up to xn. So you have n trials. Okay, and each of these x's indicates success or failure on that particular trial. So did the first trial succeed? 1 or 0, 1 for success. Second trial succeed? 1 or 0, 1 for success, and so on. Okay, so then the total number of successes, x, is equal to x1 plus x2 plus x3 plus xn. Okay, that's the total number of successes. Okay, now each trial has success probability p. Okay, so the theorem says that the expected value of the binomial random variable, so this is the binomial random variable. Okay, so this is the binomial random variable with n trials and success probability p. So the expected value of x is equal to the expected value of this sum. And the sum, expected value of a sum is the sum of the expected values. So this is the expected value of x1 plus the expected value of x2 plus and so on plus the expected value of xn. We're just applying that theorem. The expected value of a sum is the sum of the expected values. Poetry. Put it into your mind. Memorize it. Okay. But now, these are each binary or Bernoulli random variables. 1 or 0. 1 with probability p. So we computed its expected value last time. The expected value of a Bernoulli random variable is just p. P. Dot, 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 p. And so by now, we can, we're sort of experts at saying that when you add up p n times, you get n times p. The expected value of x is n times p. We derived this using a complicated sum last time. Now we got it effortlessly using the theorem about the expected value of a sum is the sum of the expected values. So this is what? It's the expected number of successes in n trials with success probability p. There, derived effortlessly. Okay. No sums. Well, we needed the expected value of the individual term, and then we used the theorem that says that the expected value of the sum is the sum of expected values. Okay. We already derived this for this important binomial random variable, which is the measurement of the number of successes in this important experiment where you try something n times with a success probability p. Okay, let's do the waiting time. Wow. We can do the waiting time? Yes, we can do the waiting time. Waiting times. Okay, so we're going to get bold. So remember that waiting process, you have a success probability p, and you keep trying until you succeed. So you're trying to access a database, and with some probability p to succeed in accessing. So you try until you succeed. You try to send a packet on the internet. You keep trying until you succeed. You try to have a girl. You keep trying until you succeed. Success probability is 1/2 in that case. Okay, and that would be definitely an interesting experiment to try. So waiting times. Now we're going to get bold. Okay, so waiting time. Waiting time. Okay, so you typically try until you succeed. We're going to even, jump straight to the most general case and consider what's the waiting time until you get k successes. So we analyze the case where, the waiting time till you get 1 success. But we could similarly say, I'm going to keep trying until I get k successes. So waiting time to k successes. So, the waiting time to 1 success, so if x1 is the waiting time to the first success. Okay. Then we showed last time that the expected value of x1 is equal to 1 over p. Okay. But what about the waiting time to k successes? So let's imagine the process where you're waiting for k successes. So you start and then you wait, okay, and you get your first success. Okay, and then you wait and then you get your second success. And then you wait and so on, your third success. And so on until you get your kth success, at which point you stop. Okay, so that's the waiting process to k successes. So let us say that you wait a time x1 for the first success, and then you wait a time x2 for the second success, and then you wait a time x3 for the third success. Okay, now let me be precise here. So the time x1 is the time you wait for the first success. The time you wait x2 is the additional time you wait for the second success. It's not the time from the beginning. And the time you wait x3 is the additional time from the second to the third success. And then you wait a time, xk, which is the additional time you wait from the k minus first success to the kth success. Okay, so the way I've defined these additional times, it's we can sort of convince ourselves that the total time you wait is just x1 plus x2 plus x3 plus up to xk. So the total time you wait, let's call that xk, let's call that x. So the total time waited, well, that's just the time you wait for the first success plus the additional time you wait from the first to the second success, plus the additional time to the third success, plus and so on, plus xk. Very interesting. Okay. So the waiting time, which is sort of, how long do I have to wait for k successes, looked like, a complicated random variable that we might find, we might have a hard time trying to analyze. But now what I succeeded in doing is to massage that total waiting time in a very quote unquote skillful way into a sum. Okay, and so that's sometimes what you have to do. You have to massage what you're analyzing. It may not obviously be the sum. So the waiting time to k successes is not obviously a sum. You have to massage it into a sum. Okay? Why are we wasting our time massaging it into a sum? So that we can apply this powerful theorem. Okay? The expected value of a sum is the sum of the expected values. Okay? I've memorized this thing since birth. Okay, so now that I've got it as a sum, we can just apply the theorem. The expected value of x is just the expected value of x1 plus the expected value of x2 plus the expected value of x3 plus up to plus the expected value of xk. Okay, and now we already agreed that the expected wait until the first success is 1 over p. Okay, and so what is the expected wait? What is the expected value of x2? Well, now let's think about it. Okay, so we've waited and we've got our first success. Okay, now we are waiting again for one success. Okay, so this x2 is exactly the expected wait for one success, where we're starting our wait at this point. Okay, and then we wait. And how long do we have to wait? Well, we wait x2. But in expectation, that's exactly the same as waiting for the first success. We're waiting for one success. So this is also 1 over p. Because we're waiting for one success. And then x3 is waiting for one success. How long do you have to wait? On average, in expectation, 1 over p. So all of these guys are 1 over p plus 1 over p. And now we're experts at this. You add 1 over p n times. This is just n over p. So the expected value of x is n over p. Oh, this is a fantastic result. What are we saying? We're saying that if you're doing this experiment where you're trying, and each time you can either succeed or fail, and you're going to keep trying until you make k successes, so then the expected time to k successes when with success probability of each trial is p. Okay, so the expected time to k successes with success probability of each trial being p is n times 1 over p. So it's just n times the weight to the first success. So let's think about it. Okay. If you're going to have children until you have 2 girls, okay, so n equals 2 girls, okay, and p equals 1/2, okay. So n times 1 over p is equal to 2 times 1 over 1/2, which is 2, equals 4. So if you're gonna have kids until you have 2 girls, you will, on average, you should expect to have 4 kids. If you're waiting to have three girls, you will on average be waiting until you have 6 kids. Okay. And the interesting question: what about the expected weight if I'm gonna have kids until I have 3 girls and 2 boys? Okay. So interesting exercise. What is the expected weight until 3 girls and 2 boys? I don't know, for whatever reason, a couple decides that they're going to have kids until they have 3 girls and 2 boys. Okay, so a problem for them would arise if they have girl. They have to keep having kids until they have 2 boys at least. Okay, they could have boy. You see the challenge. Okay, so now I want not just 3 girls but also 2 boys. What about 3 girls and 3 boys? Okay, so let's be fair. 3 girls and 3 boys. Okay. What about? Okay. So I leave these as questions for you. We'll get to that later. Challenge. Okay. Compute the PDF of X. The PDF of X. And then the expected value from the PDF. Oh, man! It can be done, but it is not easy. Okay? So compute the PDF, the number of trials, until you've gotten k successes. So that has a certain, there's a probability that it's k, then it could be k plus 1, k plus 2, and so on. So you get a PDF for this random variable x. Oh, compute the PDF for that random variable x, and then use the definition of expected value to compute this expected value directly. Well, it's a messy computation, but you will get n times 1 over p. Much easier to get from the theorem. Okay? Let me show you an amusing application of this technique for computing the expected waiting time. Okay? And it turns out, while it's amusing, it's also a very important calculation that we do and that has implications for algorithms in computer science. And it's called the coupon collector. Okay? So let's erase, and I'll come back and tell you about coupon collecting. Okay, so let me tell you about coupon collecting. Okay, so the classic example that we might hear about today, there's a box of cereal and there are 5 cartoon characters. So box has 1 of 5 cartoon characters. And if you collect all 5 cartoon characters, you get a $2 rebate. You can mail them in for a $2 rebate. So all 5 implies $2 rebate. Okay. So now you can think the process here is I'm going to buy a box of cereal. And each time I buy a box of cereal, I get 1 cartoon character. The problem is when I buy the second box of cereal, I might get the same cartoon character. So we might be interested in knowing what's the expected number of boxes of cereal I should buy, what's the waiting time in terms of boxes of cereal, okay, in order for me to collect all 5 cartoon characters, okay. Now, turns out that I was a victim of this scam when I was a kid, about 9 years old. So, in my time, you had bubblegum packs. So bubblegum, pack. And each bubblegum pack had a flag. Had one flag. okay, of approximately 169. So at that time, there were about 169 countries that had a population, greater than about 500,000. And so these countries qualified to have a flag. And so you buy a pack of bubble gum, you get a flag. Okay, and it was this huge rage in school to collect all the flags, and there were these rare flags like Brunei and all kinds of unknown countries. Okay, that it was rumored that somebody had this flag, but then we didn't know anybody who had this flag. But you were still buying packets of gum until you get all the 169 flags. You get all the 169 flags, you become the winner, the victor. Okay, and so started a craze to buy bubblegum packs. And basically this meant that, I've got very strong jaws because I've chewed a lot of bubblegum in my youth. Okay. So, each time you buy a pack, you're trying to get a flag. But the problem is that sometimes you might get the flag that you already have, so it doesn't add to your treasure chest. So you keep buying, okay? And you keep buying until you collect all the flags. So in terms of, purchasers of bubblegum packs, I'm waiting to get all 169 flags, and we might ask the question, what is the expected waiting time until I get all 169 flags? Okay. Just like what is the expected waiting time in terms of, boxes of cereal until I get all 5 cartoon characters. And so, in this case, you're clearly collecting coupons, the cartoons, and these coupons, the cartoon characters, and these coupons give you a rebate. Here, I'm also collecting coupons. The coupons are the flag, but when I collect all the 169 coupons, I don't get any money back, I just get fame. Okay. And so this is called the coupon collecting problem. I call it the coupon collecting scam. Okay. Now, what's the expected weight? So let's look at what experiment is going on. We start and we buy bubblegum packs until we get the first flag. Okay, so first flag. Okay, and let's call the weight. Let's call the weight x1. The number of bubblegum packs I need to buy until I get the first. Let's say first new flag. The first flag that I don't already have. So let me call that the first flag that's new. Okay. Can anyone guess how long I have to wait to get the first flag that I don't already have? So I'll pause the video 1, 2, 3, 4, 5. If you're coming back and you said 1, man, at least you're following the discussion. Fantastic. Okay, yes, the first pack I buy is going to give me a flag. Okay. Just like the first cereal box you buy is going to give you a cartoon character. You didn't have that before, so it's new. Okay, but now it gets interesting. Okay, now I'm going to wait and buy bubblegum packs until I get my second flag. That's new. New means I don't already have it. And then I'm going to wait. So let's call the time I wait, let's call this time x2. And then I'm going to wait a time x3 to get my third flag. Okay, so that's again a new. When I say third flag, I mean third new flag. And I keep doing this until I get my last new flag, the 169th new flag. Okay. And the question is, okay, so let's say that I wait x169. So the question is, what's the total time I wait? Well, the total time I wait, x, is same argument as we had before. It's x1, the time I wait for my first new flag, plus x2, the time I wait, the additional time I wait for my second new flag, plus x3, the additional time I wait for my third new flag, and so on. x169. Okay. And the theorem says that the expected value of this sum is the sum of the expected values. So the expected value of x is equal to the expected value of x1 plus the expected value of x2 plus the expected value of x3 plus plus the expected value of x169. Okay, but now we might think, well, the expected value of x1, well, x1 we know is 1. Okay, so the expected value of x1 is just 1. Okay, but let's try to analyze this more systematically. Okay, let's say that you are waiting for your kth new flag. Okay, so you are waiting for your kth new flag. Waiting for your kth new flag. Okay, for your kth new flag. Okay, so the interesting thing here is you've gotten k minus 1 of the varieties. You've gotten you have k minus 1 of the flags already. Okay. And so the interesting thing here is that the first flag, when you're waiting for the first flag, the probability of success, okay, with each pack you buy is basically 1. Okay, so the probability of success, P1 is equal to 1, which I'm going to choose to write as n over n. Okay. Now, let's see what's the probability of success for each of your trials when you're waiting for the second flag. So when you're waiting for the second flag, you've already gotten one flag, one variety. Okay, so there are n minus 1 varieties that you still need to get. Okay, but there are n varieties in total. So in this case, 169. Okay. So let us assume, let us assume there are n coupons. In this case, varieties of flags, and in our example, n equals 169. Okay, so after you got your first flag, that kills one of the varieties. Now you have n minus 1 to go. Okay, so when you get your next pack of gum, okay, the chances are n minus 1 divided by n that you get a new one. Okay, the chances are 1 over n that you repeat the old one that you already have. So the probability of success for each trial when you're waiting for your second flag is n, so P2 is n minus 1 over n. That's the probability of success in each trial. And you will say that you succeeded when you get your second new flag. And so your probability of success is n minus 1 over n, because you already have one flag. And each pack of gum you buy, 1 over n of 1, there's a 1 in n chance that it's a repetition of your old flag. Okay? So your success chances are quite high, but not 1 anymore. You could repeat the old flag. Okay, what about your success chances when you're waiting for the third flag? Well, you already have 2 flags, so that leaves n minus 2 flags to be gotten. So your success chances, success chances, P3, when you're waiting for your third flag, is exactly n minus 2 over n. Okay, that's your success chance. Okay, and when you're waiting for your fourth flag, it's, n minus 3 over n. And when you're waiting for your nth flag, the last flag, Pn, is equal to n minus of n minus 1 divided by n. Why n minus 1? Because you've gotten n minus 1 varieties. So every time you buy a new pack, okay, it's very likely, it's only a 1 in n chance that it's new. Okay, it's very likely that it's a repeat. Okay. And so sometimes we get this feeling that we're waiting for a long time for this last flag, and we think that they've conned us. They haven't put the last flag in any of the packets, because look, why would we have to wait so long? We only had to wait one step for the first flag, and we're going to wait so long for the last flag. Well, it's just a fact of the probabilistic analysis that you will inevitably wait a long time for the last flag, even though all flags could be equally, equally sort of distributed. Each flag is equally likely. Okay, so now we're ready to compute the expected value, because so now here you're waiting to a success where the success probability is 1. So this expected number of trials is 1 over P1. This is 1 over P1 plus 1 over P2. Now, so what's different here between the previous example of waiting to k successes? Here we're waiting for n successes, okay, where n is the number of varieties. And the success probability when you're waiting for your first success is different to the success probability when you're waiting for your second success. Okay, because the chances of your second success go down after you made your first success. And then here we have, the expected number of trials to my third success is 1 over the success probability for each of those trials. So it's 1 over P3, 1 over P n, which is 169 in this case. Okay, so this is equal to n over n, 1 over that, so n over n plus n over n minus 1, n over n minus 1 plus n over n minus 2, n over n minus 2. Okay. Plus n over n minus 3 plus plus n over n minus 1. So I've just taken the reciprocals of all these guys and added. Why did I add? That's the expected value of a sum is a sum of expected values. Now let's massage this algebraically so we can do this quickly. This is n times 1 over n plus 1 over n minus 1 plus 1 over n minus 2 plus 1 over n minus 3 plus that. And this is n times 1 over 1, which is just 1. Okay, so this is 1 plus, so this, this is the sum going backwards. Let's go forward and it'll become a lot more familiar. N times 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus plus 1 over n. Okay, and this is n. This number here, the sum of the first n reciprocals, is called the nth harmonic number. So it's n h of n. We're done. We've got a general formula. So the expected weight. Okay, so let's summarize this. The expected weight to collect n varieties of coupons is equal to n h of n, the nth harmonic number. The nth harmonic number, this is approximately equal to n log n plus, roughly speaking, n, well, there's plus n times a parameter that's called the Euler-Mascheroni constant, gamma, which is approximately 0.577, which is approximately equal to n log n plus 0.577 times n. That's your expected weight. Okay. Done. Okay, let's apply to these two examples. So first, the coupon collecting for the cartoon characters in the cereal boxes. So n equals 5. There are 5 characters of cartoons. Okay, so you need to buy approximately 5 h of 5. Okay, which is approximately 12 cereal boxes. Okay, and if each cereal box costs about $5. So cereal box costs about $5, then you're going to spend $60 in order to get a $2 rebate. Whoopee! Approximately a 3% discount. Okay. What about my days as a young kid chewing bubble gum? Okay, bubble gum. Okay. Well, in this case, n is 169, and so n h of n is approximately equal to, and that's about 965. Okay, so let's say 970. 970 packs of bubble gum will have to be purchased by me. That's a lot of chewing. So let's face it, we were really buying the bubble gum to chew. This was just an excuse. The parents are shelling out the money. We are trading flags at school. It was a royal mess. Okay, but in order to collect all 169 flags, I would have to buy, approximately 1,000 packs of bubble gum. If I bought a bubble gum pack, if I bought one a day, that would be 3 years of buying bubble gum. You see why I call it a scam? The more varieties of coupon they put in whatever game they are playing, the more you will have to buy. And this guy, n log n is growing super linearly. Okay, so this log n factor, when n is, so you think, oh, maybe I only need to buy an order of n boxes. No, the log n factor comes in. Okay, the more varieties of coupons they have. Okay, so that's the coupon collector, and I call it the coupon collecting scam. Okay, so watch out for these things. Okay, all right. So, let's move on and talk about the expected value of a product. It's a little bit more complicated than the expected value of a sum. You can read more about it in the text. Okay, I'll just quickly, summarize. So the expected value of a product. Okay. So let's consider a dice roll. So you roll a die and you get a roll. Let's call that x. So that's a random variable x. And we might ask, what's the expected value of x squared, which is the expected value of x times x, which is a product. So we might think, using the analogy with the theorem we proved, this is going to be the expected value of x times the expected value of x, okay, question mark, which would be 3.5. So the expected value of a dice roll is 3.5, 3.5 squared, and the answer is no. So it's not. So now, you can read the text about this, but I encourage you to now compute the expected value of x squared, from, we know the PDF of x, okay, so it's going to be x squared weighted by the probability of that x, so this is going to equal, it's actually equal to 1 over 6 times 1 squared plus 2 squared plus up to 6 squared. And compute it, you see it's not equal to 3.5 squared. On the other hand, if you roll 2 dice, okay, and so now you've got, the roll on the first die, which is x1, and the roll on the second die, which is x2. And so in a similar way, we could ask, what's the expected value of x1 times x2? Okay. Now, if we do this from the possible, outcomes x1 and x2, so the possible outcomes are 1 through 6, so there are 36 possible outcomes. Okay, if you go, it'll be this, from the definition of the expected value will be, 1 over 36 times, 1, so x1 can equal 1 times x2 can equal 1, plus 1 times 2, plus 1 times 3, plus 1 times 6, okay, plus 1 times, plus 2 times 1, plus 2 times 2, plus 2 times 3, plus 2 times 6, okay, plus 3 times 1, plus 3 times 2, plus 3 times 6, and we keep going up to 6 times 1, plus 6 times 2, plus 6 times 6, okay, so that's the expected value of the product of 2 independent dice, and if you compute this, you'll see that this is 1 over 36. I can factor out the 1, 2, 3, 4, and so on up to 6, and I get 1, 2, 3, 4, and so on up to 6. So this is 1 over 36, 1 plus 2 plus 3 plus up to plus 6, times 1 plus 2 plus 3 plus up to 6. Okay, because I have 1 times 1 up to 6, 1 times 1 up to 6, 2 times 1 up to 6, 2 times 1 up to 6. So you can work out this algebra. Okay, but you'll see that this is exactly equal to 1 over 6 times 1 plus 2 plus 3 plus up to 6 times 1 over 6 times 1 plus 2 plus 3 plus up to plus 6. I just broke up the 1 over 36 into 2 1 over 6s. But this is exactly the expected value of x1. And this is exactly the expected value of x2. Okay, and so this is the expected value of x1 times the expected value of x2. And wow, the expected value of the product is the product of expectations. So sometimes it works, sometimes it doesn't work. Okay, and one way in which you can be sure that it works is when you're taking the product of independent random variables. Product of independent random variables. Okay, so independent random variables are typically arising when they are the random variables that are coming from measurements of totally different, totally independent experiments. Like you roll one die and then independently roll another die. So 2 totally independent measurements. Okay. And so you can read the text about more details. So the expected value of a product is only the product of expected values for independent random variables. Okay, we're going to move on to show you some techniques that use the law of total expectation, and then we want to introduce indicator random variables. Okay, so let's talk about total expectation and build up expectation. I'm now going to tell you about some applications of the law of total expectation, that very powerful, technique that we can use to simplify expectations. Okay, now, law of total expectation. Okay, now, one reformulation of the law of total expectation leads us to a tool or a concept called iterated expectation. Okay, so iterated expectation. And I'm not going to cover that here. You can read all about it in the text. Okay, so see text. Okay. What I'm going to talk about is the application of the law of total expectation to build up expectation. So, just like we had build-up counting, it's possible to compute expectations by starting small and building up to larger problems. Okay. So we will showcase this with a very specific example, but just let me remind you what the law of total expectation is. So you're computing the expected value of a random variable x, okay, and you break it down into two cases, case A and case not A. And, it's kind of a case-by-case analysis. So the expected value of x is the expected value of x conditioned on being in case A, weighted by the probability of being in case A, plus the expected value of x conditioned on being in case not A times weighted by the probability of not A. Okay. So it's not just the sum of conditional expectations. You have to weight by the appropriate probabilities. Okay. Now, we studied the waiting time to K boys, and we studied the waiting time, and that equivalently can be the waiting time to K girls. Okay. So, the waiting time to K boys is equal to, so you're waiting for K successes. Think of a boy as a success, and the probability of success is 1/2. So it's K over 1/2. We derive this, so that's 2K. And the waiting time to K, to let's say L girls. Now think of the girl as the success. The probability of a girl is 1/2. So it's going to equal L over 1/2, L over the probability of success, which is again 2L. No surprise. The waiting time, the expected wait for K boys is twice the number of boys you're waiting for. And the waiting time, the expected number of kids to L girls is twice the number of girls. But now let's add a twist. Supposing you're going to have kids until you have, 3 boys and 3 girls. So the waiting time to 3 boys and 3 girls is what? So you could have boy, 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 then girl, 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 and that now you've gotten, you could have more than 3 boys, okay, but you're still waiting because you're also waiting for 3 girls. Okay, this is more complicated. It's actually a lot more complicated, but we can solve it with the build-up method. Okay, and the general idea when you're using the build-up method is you start, from some more complex problem and try to reduce it to a simpler problem. And when you're analyzing this reduction, this recursion, so to speak, it helps to sort of consider the general case of a bigger problem and try to reduce it to an instance of the smaller problem. So let us consider the waiting time to K boys and L girls. So the most general version of this problem. Here you're waiting for K boys, only boys. Here you're only interested in girls, so you're waiting for L girls. Okay. Here it's specific, 3 boys and 3 girls. But look at the general problem, waiting for K boys and K girls. Okay. And it's useful to give this a notation. Let's call this the waiting time W for K boys and L girls. Okay. So it's always useful when you're doing build-up to have a notation for the thing you're trying to compute, and then we're going to try to now relate this to smaller values of K and L. So for example, let's start with some easy cases. You're waiting for K boys and 0 girls. Well, we just computed that. That's waiting for K boys. Okay, so that's 2K. You're waiting for 0 boys and L girls. Well, we computed that. The waiting time to L girls. That's 2L. Now let's see if we can analyze in general. So remember, this is the expected waiting time. Sorry, I should say the expected. And in all cases, it's the expected. It's the expected. It's the expected. So we're talking about expected values. Okay. So what is the expected waiting time, to K boys and K girls? So the expected waiting time, waiting time for K boys and L girls. Now we just use the law of total expectation. It says it's the expected weight, the expected value of the weight, given that the first child is a boy. So case 1, case A, the first child is a boy, times the probability that the first child is a boy, plus the expected weight, given that the first child is not a boy, i.e. a girl, times the probability that the first child is a girl. Okay? Well, let's see. What's the okay, so this is a half. 1/2. This is a half. 1/2. Okay. What is the expected weight given that the first child is a boy? Okay, well, you've had one child, which is the boy, so you have one child, okay? And now you're waiting for what? You started waiting for K boys and L girls. You've had one boy, so that's one child, plus you're going to be waiting for K minus 1 boys and L girls, because you've had a boy. This is going to be 1 plus W of K minus 1 and L. The expected waiting time to K minus 1 boys, because you've had a boy, and L girls, because you were originally waiting for L girls. Okay. And this guy here is 1 plus the waiting time to the K boys you were originally waiting for, but you had a girl. So that's this 1. Okay. Now you're waiting for K boys and L minus 1 girls. Okay. And this guy here is exactly W of K and L. Okay. So what have we proved? W of K and L is equal to 1 plus W K minus 1 L times a half plus 1 plus W K L minus 1 times a half, which is equal to, so W of K and L is equal to 1 times a half plus 1 times a half is 1 plus 1 half W of K minus 1 L plus 1 half W of K L minus 1. Bam! That's it. There's our build-up recursion. It tells us how to compute the expected waiting time to K boys and L girls. It doesn't actually tell us how to compute it. It just says it's related to smaller problems. Waiting for K minus 1 boys and L girls, or waiting for K boys and L minus 1 girls. Okay. So let's see how we can use this to compute the expected wait to 3 boys and 3 girls. Okay. So, let me put K here. That's the number of boys you're waiting for. And L here. So you could be waiting for 0 boys, 1 boy, 2, 3, and so on. You could be waiting for 0 girls, 1 girl, 2 girls, 3 girls, 4 girls, and so on. If you're waiting for 0 boys, okay, so the waiting time for 0 boys and any number of girls is just twice the number of girls. So you don't have to wait at all if you're interested in no kids. You're done. Okay? If you're waiting for 1 girl and 0 boys, you wait on average 2 kids. On average 4 kids, on average 6 kids, 8, and so on. Okay. On the other hand, if it's 0 girls and you're waiting for K boys, on average, if it's 1 boy, 2 kids, 2 boys, 4 kids, 3 boys, 6 kids. Okay. Now, let's see what this is saying. What this recursion says is, let's say we're interested in 2 boys and 1 girl. It says, you take 1, okay, and you're going to take the average, so 1 half of this sum. What is this sum? That's 1 half of, it's the average of these 2. Okay, this is K minus 1, so you go up in K. So you go up in K, and you go L minus 1, so you go left in L. So you go left in L. You take the average and add 1. So this is going to be 3. Take the average and add 1. So the average of these is 3.5. So you add 1, 4.5. Take the average and add 1, 5.25. 0.25. Okay, so this is going to be, take the average and add 1. So 5.25, 6.25. Okay. Take the average and add 1. So 3.5, 4.5. Okay. Take the average and add 1. So 5.5. Okay. Take the average and add 1. So here we're going to have 6.25. Okay, and we're getting there. Okay, now take the average and add 1. So this is 8.875. Sorry, 6.875. Okay, and the same thing here, 6.875. Take the average and add 1, so 7.875. Bam! Look at that! Such an odd number of children. Okay, I'm just using this recursion to build up, to fill in this table. Okay, and what we observe is that when you grow up, and you get married, and you're deciding to have kids, and if you're waiting, and you'll continue to have kids until you have 3 boys and 3 girls. I don't know who's going to do that, but, let's say you do. You're expecting to have, a little under 8 kids to get 3 boys and 3 girls. So let's say 8 kids. So I expect to have 8 kids. Okay. So that's an example of the build-up method for computing expectations. Now, I want to tell you about indicator random variables. And when used with this theorem on the expected value of a sum is the sum of expected values, very powerful, very surprising, very stunning results can pop up. Indicator random variables. indicator random variables. So again, we're talking about not new concepts, we're still talking about expected values. It's just different tools and techniques. So, we saw linearity of a sum and how that can be useful. We saw build-up counting, okay? And now indicator random variables. Okay. So the idea here is, and the indicator random variable is a very sophisticated name. It's just another way of referring to the Bernoulli, the guy that's either 0 or 1, the binary random variable. 0 means I failed, or 1 means I succeeded. Now, you're interested in some random variable x. And the idea here is that if you can in some, sly way represent x as a sum of indicator random variables, okay, then you can compute the expected value of x using this theorem as the sum of the expected values of those indicators, those binary random variables. And the expected value of a binary random variable is easy to compute. If it's 1 with probability p, the expected value is just p. So computing the expected value of each of the indicators just amounts to computing the probability that each of those indicators is 1. And if they have different probabilities, then you have to compute a different probability for each of them. But once you have those probabilities, you just add. Okay, so let's see this technique in action. So 4 people, and I'm just going to label them by colors. So blue, okay, and they're square people. So blue, red, green, and black. They're graduating, so they all throw their hats in the air, and the hats land randomly on heads. And so you can imagine that, some assortment of hats, lands on the heads of these people, and some of them get their correct hat, and some of them do not. Okay. So, maybe the black hat miraculously lands on the black guy's head. The blue hat lands on the red guy's head. The green hat lands on the blue guy's head. Okay, and the red hat lands on the red guy's head. Okay, and so in this example, we can see that one person got their correct hat, and the other 3 got incorrect hats. And so the question we're going to ask is, when you do this experiment, when you randomly throw up the hats and the hats land randomly on people's heads, what is the expected number of people to get the right hat? Okay, now, hard exercise. So this is an experiment, and the random variable we're interested in is the number of people who get the right hat. Let's call it k. Sit down and see if you can compute the probability distribution for k, the PDF for k, this random variable. And then from the PDF, compute the expected value. That's a hard problem, okay? And you can see the text for that computation. I'm going to show you that if we're not interested in the PDF, if all we want is the expected value, we can get it very easily. So let x equals the number of people who get the right hat, and we are interested in the expected value of x, i.e. the expected number of people who get the right hat. Okay. Now you might wonder, wow, this is going to be complicated. How am I going to do this? And what's this theorem about the expected value of a sum doing here? Okay, how's that going to help us? Well, so this is where the trick comes with using indicator random variables, is to say, well, let me define an indicator random variable. So x1, okay, which indicates whether the blue guy got his correct hat. Okay, so x1 equals 1 if he got his correct hat, and 0 if he did not get his correct hat. Similarly, I can define x2, which is equal to 1 or 0, depending on whether he got the correct hat. And this guy is going to so x3 equals 0 or 1, depending on whether he got the correct hat, and x4 is either 0 or 1, depending on whether he got the correct hat. So let's see what are the values of these indicators for this example. So x1 equals 0 because he did not get the right hat. x2 equals 0 because he did not get the right hat. x3 equals 0 because he did not get the right hat. And x4 equals 1 because he got the right hat. Okay. Now, how many people got the right hat? So x, okay, is just 0 plus 0 plus 0 plus 1. The number of people that got the right hat is just 0 plus 0 plus 0 plus 1. So if you add up the indicators of whether each person got their right hat or not, if you add that up, it gives you the total number of people who got the right hat. Okay? And this is generally how we use indicator random variables. We're trying to count something, okay? And what we're trying to count is made up of a bunch of things. So we indicate whether or not each of those things occurred with an indicator random variable and add the indicator random variables. Okay? So if I want to know how many students have brown hair, I can define an indicator random variable, which is 1 if you have brown hair and 0 if you don't. I figure out the indicator random variables for each person and just add. That'll tell me the number of people with brown hair. Okay. So in general, the number of people who get the right hat, x, is equal to x1 plus x2 plus x3 plus x4. Okay. And so there we are ready to apply the theorem. The expected number of people who get the right hat, expected value of x, is the expected value of x1 plus the expected value of x2, expected value of x3, plus the expected value of x4. And now we need to compute these expectations, which amounts to computing that the probability that x1 is 1. What's the success probability for x2? Success probability for x3, success probability for x4. Okay, but now let's think about this. Everyone throws the hat and one of them lands on blue. Okay, so, and since there are 4 hats and only one of them is blue, there's a 1 in 4 chance that that the blue guy gets his right hat. So there's a 1 in 4 chance that x1 is 1. So P1, probability that x1 equals 1 is equal to 1 in 4. Okay? But if you think about it, there's no difference between the blue guy and all the other guys. Each of them gets their right hat, and the chances are 1 in 4, because they're going to get one random hat out of 4. Okay? So the probability that x2 equals 1 is also 1 in 4. Probability that x3 equals 1 is also 1 in 4. Probability that x4 equals 1 is also 1 in 4. So they're all 1 in 4. And the expected value of a binary, of an indicator, of a Bernoulli random variable is just the probability of success. So this is 1/4, 1/4, 1/4, and 1/4. And when you add up 4 1/4, well, we all knew how to do that from H2. This is 1. So the expected value of x is 1. So the expected number of people who get their correct hat back is 1. Okay, so quick exercise. What if you did this with n people and their n hats? What if there are n people? So pause the video, work it out. Same method, work it out. I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay, now if you're coming back just for the ride, or if you said that the expected number of people who get their right hat back is 1, you're on the money. You know how to throw hats up in the air and compute the expected number of hats landing on heads. And now that's interesting. The ease with which we get that is just the same argument, but except that there'll be n terms here, and each of them will be 1 over n, so n times 1 over n is 1. This is an interesting conclusion. You might think that the more people there are, the more likely it is that more people on average will get their right hat. Okay, but there's a trade-off. The more people there are, yes, there are more chances to get the right hat, but each person gets their right hat with a lower probability and they exactly balance. And so only on average 1 person will get the right hat. Interesting. Okay. So let me erase, and I'm going to show you another cute application of indicators and taking the sum of indicators. Here's a quick application of indicator random variables to get a result that would otherwise not be so easy to get. Okay, so we're going to use indicator random variables and linearity of expectation. And we're going to analyze record breaking. So, record breaking. So pick your favorite sport or just your favorite thing that you're interested in. For example, daily temperatures in Troy, or the 100-meter, record, or the women's freestyle, 5,000-meter, record. Okay, so let's imagine that it's attempted. So there's an event where you can measure this quantity, whether it's the temperature in Troy on a given day, or the women's 5,000-meter breaststroke race, or the men's 100-meter sprint. Okay, so you measure. Oh, it's a record. Okay. Okay. Well, the first time the event happens, it has to be a record. But now you measure. It's the best, that has been seen so far. Okay, so that's a record, new record. Then, the thing happens, new record. Thing happens, new record, and so on. Okay. So every now and again, the record gets broken. And we might ask, if we go through history as a function of time, how many records are broken as there are more and more trials? Okay. How many records will be, how many times will the record be broken? So let's take an example. Okay. Let's take the daily temperature in Troy. Okay. So you have, starting from, let's say, way back when temperatures were recorded, there's T1, T2, T3, T4, T5, and so on, up to Tn. Okay, so the temperatures, let's say it has happened n times. We've measured the temperature. So that's a trial. Okay, and just to simplify things, let's assume that these temperatures are all distinct. So it's never going to be the case that you have the exact same temperature on, let's say, high, the exact same high on a particular day, the exact same high. Okay, and there's no reason to believe that any one day is preferred to another. So let's assume that these temperatures are just randomly ordered. So you've got a random ordering of some temperatures. Okay. Now on the first day, so I'll highlight the days that are record. So the first day is clearly a record, because that's the first measurement. Okay, and then maybe there's a record on another day, and then a record on another day, and so on. And so in this case, we will say that a daily high temperature, a record-breaking temperature was achieved on these red days. What that means is it's a temperature that's larger than all previous days. Okay, and in this case, the record was broken 4 times. And we might be interested on average, what's the expected number of times the record will be broken? That looks like a very, very complicated thing to analyze. Once you break it down using indicator random variables, it just reveals its secrets. Okay, so here we go. We will define an indicator which says, was today a record or not? So x1 equals 1, because it was a record. In this case, x2 equals 0, not a record. That means it was less than T1. x3 equals 0, not a record. x4 equals 1, yes, record. x5 equals 0, not a record, and so on up to xn. So xi indicates 1 if day I is a record, and 0 if day I is not a record. Okay, interesting. Okay, so now let's see, what's the probability that day I is a record? So what's the probability that xi equals 1? So let's think about it. You've got x1, x2, you've got the temperatures, T1, T2, T3, up to Ti. Okay? And we said that these are all distinct temperatures and they're randomly ordered. So there's one maximum, and what is the chance that that maximum is on day I? Well, the maximum, the largest of these temperatures, is equally likely to occur on any of these I days. So the chances that the maximum occurs on day I is 1 in I. Okay? So the probability that this temperature is a high is 1 over I. So that's the probability that xi, that indicates if it's a high, will be 1. So this is 1 with probability 1 over I, and 0 otherwise. Is 1 with probability, and 0, it's an indicator with probability 1 minus 1 over I. So the probability of success for this indicator random variable is 1 over I. Okay, and that's interesting. So what it's saying is that as you move further and further away from the beginning, the chances are less and less that it is a record, and that's natural. Because as you move further and further away, your temperature has to beat all the previous. In other words, the maximum must be u, which is a 1 in I chance. Okay, and so, the first day is guaranteed to be a record. Probability 1 over 1. The second day with probability 1/2 is a record, because, these two temperatures are randomly ordered. And so this guy has half the chance of being the largest, and so on. Okay, well, how many times was the record broken? It's just the sum of the xi's. So the number of times record broken is equal to x1 plus x2 plus xn. There comes the theorem with indicator random variables. So you just have to be skillful in identifying the indicator and then computing, what you want in terms of a sum of indicators. So the expected number of times record broken is equal to the expected value of x1 plus the expected value of x2 plus, that's the theorem at work, expected value of a sum of expected values plus the expected value of xn. So we just need to compute the probabilities of success for each of these indicators, but we just did that. The probability of success for each indicator xi is just 1 over I. So this is 1 over 1, which is 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus that, plus 1 over n, which is just hn, the harmonic number. Wow, this harmonic number popping up all over the place. It's already popped up twice today. Already popped up when we did coupon collecting. Now it's popping up for record breaking. Okay? And this, for all of you who sort of, well versed in the harmonic numbers, and we had some exercises on induction to prove things about this, and even the integration method can give you, bounds for this sum. So this is approximately log of n plus a constant plus, 0.577, and this is a constant that is called the Euler-Mascheroni constant. Okay. Punchline. The number of records that you will see broken up to time step n is growing like logarithm of n, much slower than n. Okay, and so very much slower than n. So if you take this logarithm of n, if you take all temperatures in Troy, let's say for all of recorded history, you'll find that this is predicting about 6 or 7 times that you have the all-time high, and indeed. When you go into the almanac, you will find that it is 6 or 7 times. Remarkably accurate. Wow. Take your favorite sport, whether it's 100-meter sprints or the 5,000-meter freestyle women's, race or whatever you want. And you need to be able to compute up until today, how many trials were there, and then take the logarithm of that. Bam! You got the number of times the record breaker. Go and look and see in whatever area of interest you like, if you plot time and you see, how many times was the record broken, it'll be growing like the log of n. This is a universal phenomenon that record breaking occurs at a rate of log n when you do n trials. Wow! Isn't that impressive? Okay, so today we continue the discussion of the expected value, and in particular, we used all kinds of fancy tricks and tools to make computing expected values easier, indicate random variables, build up counting, but most importantly, the linearity of expectation. And so I keep telling you, memorize this poem. The expected value of a sum is the sum of the expected values. It's not really a poem. Memorize it anyway. Checking out. See you next time.